There's two types of problems on the ramp friction worksheet. On this video, I'm going to go over the first type of problem. First thing I need to point out is that for every problem, you need to show all work on a separate sheet of paper and staple to the back. Calculators are allowed, but write out all steps. Round your answers to two significant figures. Draw a free body diagram for all problems. Don't forget your units. Problems 1 through 4 are all the same, but the first thing that I need you to do is go to number 1, and let's go ahead and let's change this to an angle of 1 degree instead of 0. It makes it a little bit more interesting to do 1 degree. Okay, so again, what we've got, an object on a ramp sliding down. We're calculating for mu, just as we've done with in our lab. So first thing I'm going to do is transfer all this information to my blank sheet of paper, so that I can turn everything in together and my teacher will be extremely happy with me. So, problem number 1. Given information, we are first given theta equals 1 degree. We are given a mass of 0.5 kilograms. And we want to know the force of weight. We want to know in newtons. We want to know the force of weight in pounds, just to show you the comparison there. That's the only reason I'm having you do that. We want to know the force of friction, and we want to know the normal force. Gosh, you got to earn that epoxy label, don't you? Lastly, we need to find mu, the coefficient of friction. How sticky is it? So first thing I'm going to do is I'm going to draw my picture. I'm going to draw my plane. I'm going to exaggerate this 1 degree here. I'm going to go ahead and call that theta because it makes it a little bit easier to see if you exaggerate the angle a little bit. I'm going to draw my box right up here, and I will put the force of gravity on it just as we did in our lab. And so the force of gravity might be the first thing that we solve for. So since it's the first thing that's asked for, force of gravity, which is the same thing as the force of weight, we all know that, mass times acceleration due to gravity, 0.5 kilograms from my given information, times 9.81 meters per second squared, acceleration due to gravity on Earth. And when I get out my calculator, 0.5 times 9.81, 4.905. So the force of gravity here is 4.91 newtons. I can do that because in the instructions it said round to 2 decimal points. So I can come right back over here, 4.91 newtons. Now, I'm going to box that in. Important information. To change from newtons to pounds, just to give you an idea of what we're talking about here, is pretty simple. You just take 4.91 newtons, and because there are 4.4 newtons in 1 pound, you're going to divide so that the newtons cancel out, and we're left with pounds. So we go 4.905 divided by 4.4. So that is equal. So 4.9 newtons is about the same as 1.11 pound. So there you go, just to give you an idea of what we're dealing with here, 1.11, which is about the weight of actually some of those sliding blocks that we've been using in class. Okay, now onto the more interesting stuff. Solving for the force of friction and the normal force. Just as we've done before, we've got to take this and we've got to break it into the two components that make up this force of gravity, this weight component. Remember, this one is going to give us the normal force because this is how hard the force of gravity is pushing the block into the board. And this one's going to give us the pulling force, or the force of friction, because it's telling us how much of this, what component of this vector is pushing it down the ramp. So this is our angle theta that we got here that is given to us on this problem. And so we're going to call this FGY, and we're going to call this one FGX. Actually, let's go ahead. Let's call this the normal force, and let's call this the force of friction. They are actually the opposites of that, but what the heck? That's what we're really getting at in the end. So, because this normal force is going to be the adjacent to our angle, we're going to use our cosine function. So if we come down here and find some space, we can say cosine theta is equal to adjacent over hypotenuse. Start plugging in numbers now. Theta we know is 1, so cosine of 1 degree, and make sure your calculator's in degrees. The adjacent is what we don't know. That's going to be our normal force divided by the hypotenuse, which in this case, our hypotenuse is the force of gravity. So the force of gravity, which we've calculated, is 4.91 newtons. So now, algebraically, we're going to multiply this side by 4.91, and what you do to one side, you got to do the other. So we have the equation, the normal force is equal to 4.91 cosine of 1 degree. So now I'm going to go back to my calculator and start to plug this in. I'm going to start with 1 degree. Cosine of 1 degree is 0.99 times 4.91 is going to be 4.9. Let's call it 4.90 for the sake of this. So what you're going to see here is that since it's only 1 degree, and this should start to make a little bit of sense now, since this angle is only 1 degree, it's basically just like those initial problems where all of the force of gravity is pushing into the board, because there's not much lift on that board yet at all. So let's just call this 4.90 newtons. Now, to solve for the force of friction, which we said is going to be this component right here, we're going to have to use their sine function. So we're going to say sine theta is equal to opposite over hypotenuse. And now we can plug in the numbers that we know. And actually, I'm going to take 2 steps here in one, and I'm going to say the force of gravity times sine theta is equal to our force of friction. So 4.91 newtons times sine of 1 degree equals, and I go back to my calculator, 1 sine of 1 is equal to 0.017 times 4.91, and if you could anticipate this number, you're going to anticipate that it's going to be very, what do you think, big or small? That's very small, that's right. 0.09 newtons. So basically nothing is pushing it down the ramp at this point, and that's why most of them wouldn't slide at 1 degree, unless maybe it was on ice or something. So this is our force of friction. Let's box this one in. Let's box this one in. And then lastly, we're going to solve for mu. Going back to our fun equation, force of friction is mu times the normal force. Mu is equal to the force of friction divided by the normal force. We found our force of friction, 0.09 newtons, and our normal force, 4.9 newtons. And so you would expect for this to have if it slides at 1 degree, its mu, its stickiness is going to be really small, which 0.09 divided by 4.9, go figure, mu is 0.017, not sticky at all. Now we're just going to go back to our sheet and plug in our numbers. Mu is 0.017 0.017, so I'll come over here, mu 0.017. Because that one's so small, I'm going to 3 decimal points. Our normal force was 4.90. Our force of friction was 0.09. Our weight in pounds, 1.11. And our weight in newtons, 4.91. And so we've got problem number 1 completed.